All right, this unit is all about transformations and what different transformations do to a function or how it looks. The first thing, before we actually look at any transformations though, we're just going to kind of play around in Desmos. So first off, I want to look at this function. Now notice I have it written in function notation. F of x equals a times the amount x plus b, that all in parentheses, plus c. So I'm going to set c to 0 and b to 0 and a to 1. Notice that means this is just a linear function. It makes a perfectly straight line. If a is 1, 1 times this whole thing, x plus b, well, x plus 0, it's just x. This is going to come out to be, maybe I'll just write another one down here, y equals x. This one in red and this one in green here, these two here and at the very top, it's the same exact thing. Okay, I'll get rid of this. Oops, I mean to zoom in. I'll get rid of that linear one now, but this is just a linear equation. Now notice I have this thing A, this thing B, and this thing C that I can kind of play around with. And as I play, it will change these things. So if I change A, notice this is the thing out in front that tilts everything. Now that should make sense because what I'm doing here when I play with A, I'm increasing or decreasing the slope. Here is my slope of the graph, AX, or we usually think of it as y equals mx plus b. So here is my slope. This last one, c, would be my y-intercept. So notice when I bring it down, it goes down. When I bring it up, it goes up. As all of these things change, these are what we call transformations. We are changing this graph. We are transforming it by just kind of sliding it around or tilting it or whatever you might want to consider these things. We are transforming the graph using these different values. Now, it's not just linear equations, these lines that would do that. We've also looked at absolute value functions this year. Now again, notice I have a out front. My a value is 2. If I make a really big, it's going to narrow that V shape. If I make it smaller, notice how it's getting wider and wider and wider. I get it to 1. That's kind of our normal V shape. Actually, I should get this up to 0. There, now that is our perfect parent function of the absolute value. It's a perfect V centered right here at the origin, 0, 0. Now if I play with that A, if I make it go smaller, notice how wide it gets. If I have it go bigger, notice how narrow it gets. Now I can get it so small that it even goes negative. When it is negative, notice it's pointing downwards. Now a bigger negative makes it narrow, but pointing downwards. And a negative that's less than 1, again, just makes it wider. Okay, I'm going to bring it back to 1. Now this B value in my absolute value, notice that all it is doing is sliding that vertex left and right. The C value, again, is always that y-intercept. So notice it's going to bring that up and down. Now if I do a couple things, if I bring my C value up and my B value down, notice from this original origin, it's both up and to the right. So I can change both my C and my B value. If I wanted to, let's see, I'm going to get this back to 0, back to 0. I could change my B value. So now it is to the left. I could change my A value. So now it is narrow, and my C value. So now it is further down. So I can change all of those things. Now, if I don't want to be looking just at the absolute value, I can also do this, again, with our parabolas, things that we've worked with during our quadratics. Again, this B value will shift everything sideways. C value shifts everything up and down. A value will narrow our parabola or widen it. Okay. Now notice that the parabola, our quadratic one, this is vertex form. Okay, we have a times the amount x minus h squared and then plus k. Okay, so b and c, these help you find your vertex. It's minus h plus k, or in our case we said plus b and plus c. So it'll be the opposite of b. So if I set b to, I'm going to set b to 1 and set b to negative 2. Then I should be at negative 1, negative 2 for my vertex. There it is, negative 1, negative 2. And again, that a value is what's going to narrow or widen the graph. Okay, all of these playing around, all of these kind of manipulating our values, these are transformations. This is how you transform things. And that's what we're talking about this week, is transformations of our functions. So I'm going to talk about or look at a couple different kinds of transformations. Now there are three main transformations we're going to be looking at. A translation is a slide. You are moving everything entirely up and down or left and right. Suppose I could put a, there we go, up, down, left, right. That is called a translation or a slide transformation. A reflection is a flip. You're going to flip or mirror the graph about an axis, usually the x-axis or the y-axis. Lastly, there's a dilation. You are going to stretch or shrink the entire function vertically or horizontally. So translation, reflection, and dilation. These are the three kinds of transformations that we will be looking at. The first couple that we're going to look at are a few different kinds of translations, a few different of the slide kinds. So, a couple of the rules to look at. If you are given any function, f of x, and all of a sudden you are changing it by taking that f of x and you're adding a certain number, I'm going to call it k. If you're adding k onto the old function, this will move the function up k number of units. And for example, if my f of x is 3x plus 4, to go from 3x plus 4 to 3x plus 6, all I had to do was add 2. I took this entire function and I added 2 to the end of it, or like f of x plus 2 more. So I added 2 on, just like add k, so I'm going up 2 units. Again, if we wanted to look at that, we would say, all right, here is y equals 3x plus 4. I also have 3x plus a. I can slide this up and down. This piece, this a, determines the y-intercept of the line. So if I want to go up 2 units from here, I just move this up to, oops, right there, 6. It's the exact same line, just moved up from here to here, 2 units up. Same thing, if I do f of x minus k, the whole function will move down k number of units. So to go from 3x plus 4 down to 3x plus 1, I had to subtract 3 from that, or f of x minus 3. I'm subtracting 3 to go down. So on here, it would look like instead of plus 4, this should be down at a plus, too far, 1. So again, normally it was supposed to be here. It's now down here. It's the same exact line. Everything just shifted down 3 units. Now, if I'm just looking at my x, so not the entire function, just my input x, and I'm adding or subtracting to it, that's going to move things left and right. It's still a translation, but instead of up and down, it's left and right. So if I have f of x plus h, notice that the f of this h is inside of my input value. So the whole function will move h units to the left. If you're adding it on, you're going to the left. Okay, I'm going to show you how or why that looks. Again, if we start with that 3x plus 4, but my input x, I'm going to add 2 onto that. So again, it would look something like this. F of x plus 2. and that plus 2 is inside the parentheses with this x. That means I'm going x plus 2 right here. Now when I distribute that 3, it'll say 3x plus 6, and I'm still adding the 4, so it's actually 3x plus 10. So if I were to go and look at that at Desmos, on here I would need this to be a 10. So if we think of it as here was my original one, I actually just slid everything over 2 units. 2 units to the left, so 1, 2 units right here to the left. I know it looks like the same as going, oh, it was up 6 units, but this was actually moving left, if I can get it to the right spot, left 2 units. Kind of hard to see it with linear. If you do it with a quadratic or a absolute value, it'll be a little more exact. Same thing, if I do a plus h and make it go left, if I do a minus h, it'll go right. So again, if I did x minus 5, distribute that 3, it would say 3x minus 15. Combine these two, 3x minus 11. Everything would just be shifting downwards. So this would then be 3x minus 11. It looks like it's all shifting from here over to the right 5 units. So that would be all of our translations. You can translate up and down. You can translate left and right. Let's look at some of our other transformations, our dilations. So we can stretch things and shrink them vertically. Now if you take your whole function and you multiply it by a number on the outside of the entire function, that will stretch things vertically. So again, to look at an example, if I started with that 3x plus 4 and I multiply the entire function times 3, right? 3 times 3x is 9x, 3 times 4 is 12. It's the same exact line, it's just stretched vertically. So from 3x plus 4 to 9x plus 12. Oops. Plus 12. So the whole thing got stretched vertically. There isn't necessarily always going to be a point around where it is stretched. I think for the most part you can usually consider it the x-intercept is kind of where everything is centering at, but then everything was stretched then vertically. So instead of going just up so much, it goes up a lot. Instead of going down so much, it goes down a lot. Everything was stretched vertically from this x-intercept. Same thing, if I do a smaller number, so this s out front was a big number, I'm going to use a fraction. Now it doesn't have to be 1 over something, but I'm going to pretend that it is, in this case, a small fraction that's less than 1. So I'm going to make my numerator be 1 over s. Now it can be anything as long as it's smaller than 1. So like 2/3 is less than 1. So 2/3 would still shrink this vertically. So we don't have to use 1 over s. I'm just using that to show you that's what makes it shrink. So in this case, I'm going to multiply all of this times 1/2. Again, I'm using a half. I'm using a small fraction, something less than 1. So half of 3x would be 3/2 x. Half of 4 would be 2. So 3/2 x plus 2 would be our new one. So 3/2 x plus 2. Again, notice that it all stays right here at this x-intercept, but the blue one actually came down from this. Right? We're shrinking everything vertically. Instead of coming up all the way to 4, it's actually only going up to 2. Instead of going way down, it's only going somewhat down. Right? So it's all staying around this x-intercept and then stretching or shrinking based on the number that you're multiplying the entire function by. The other kinds of dilations would be to stretch or shrink things horizontally. Now again, we have to look at things inside of our input. So we have to do something times just the x, not times the entire function, just times the x. So if I do something times x inside of my input value here, and it is a large number, something bigger than 1, it will shrink everything horizontally. So even though bigger number here, this will actually get smaller horizontally. Okay, so again, if I have f of x equals 3x plus 4, but instead of an x, I'm plugging in 2x. Right, so I'm plugging in something a little bit bigger, something 2 times this big. So I have to distribute that. 3 times the 2x makes 6x plus 4. So it would look something like this. Notice that on the last one, they shared the same x-intercept. These ones will share the same y-intercept. Now the red one was what we normally were before. This blue one, you can see it shrunk horizontally. Instead of going out so far, it's only going out this far. Right, from here to here, it should be coming over 2, but it's actually only coming over 1 to get just as high. Same thing, if I'm moving over, let's say 1. Here, it didn't take as long to move over 1. Here, it's taking a lot longer, right? So it's shrinking everything horizontally on our left and right scale. Same thing if I'm multiplying it by a fraction. So instead of a large number, multiply it by a small number, it's going to stretch things horizontally, make them grow faster. So if I multiplied just this piece, instead of 3 times x, I did 3 times 2/3 x, and then added 4. Well, 3 times 2/3 is just 2. 2x plus 4 would make it look something like this. Notice it's stretching everything. So instead of being this red line, it's stretching out further horizontally, stretching outward more. The last kinds of transformations I want to look at are our reflections. And again, you have two different kinds. One's where you're looking at the input on the inside here. One's where you're looking at the entire function. Now, if your input is negative, so instead of f of x, we want f of negative x. We're just turning only our x value to be a negative. That's when you're going to reflect over the y-axis. And then so actually, I got to fix this. This should be the exact same thing. So instead of 3x plus 4, it's negative 3x plus 4, because just the x piece was made negative. 3 times negative x is negative 3x plus the 4 still. It's reflecting over the y-axis. So it would look something like this. Here's our y-axis. The red line was our original line. This blue line looks the exact same if it were held up to a mirror. And the mirror was held right here on the y-axis. Now let's say I multiplied the entire function by negative. That reflects it over the x-axis. Oops, I got to fix this one too. The entire function then becomes negative. So instead of f of x being 3x plus 4, I make everything the opposite, so negative 3x minus 4. It's going to be the same exact line, only reflected over the x-axis. So I just have to change this to a negative 4. Again, there's still a mirror here. My mirror is just here on the x-axis, not on the y-axis. It's flipped over this one. So again, if it's on the inside, it's just reflecting over the y-axis. On the outside, it's reflecting over the x-axis. That'll cover for video 1. We've discussed transformations and what the transformations will look like in function notation.